All right, so welcome to another lecture for linear algebra. Today we're learning about matrices, some super basic things. For example, we hope to learn the basic definition of a matrix, how to add them, how to multiply matrices, and maybe how to do scalar multiplication of a matrix. So first things first, a matrix. Really, a good way to think about a matrix is a table with entries. That's it. That's pretty much a matrix is. It's a table with numbers or entries. They don't always have to be numbers. They could be functions. They could be matrices. They could be cats and dogs. They could be anything. It's just the big defining features is the fact that it's a table, meaning that it has a certain number of rows and a certain number of columns, and the entries are lined up as they would in a table. For example, here's a simple example. Suppose I have a table here with few numbers 2, 3, 5, 1, 0, -1. This would be a table of numbers. And these numbers all happen to be integers. These are all integers. If you remember from our last lecture, the symbol for integers would be this fancy Z. This also happens to have, let me see, 2 rows. And it also happens to have 3 columns. So one way to think about it, a short way notation is that let's call this number A, this matrix A. It's customary to refer to matrices using a capital Roman letter, like we'll call this A. This is a matrix A. A is equal to that. A fancy way to encapsulate all of this, the fact that it's got integer coefficients, integer entries, it's got 2 rows and it's got 3 columns. The fancy way to encapsulate all of that and the fact that it's a matrix is to just say that we would say something like this. A is an element of the family of matrices that are 2 by 3, meaning they have 2 rows and 3 columns. That's where you get this 2, 3. The first one is the number of rows. The second one is the number of columns. The M stands for matrices. The E here means element of. So we're saying A is an element of the collection of all matrices that are 2 by 3 and that have integer entries. So I could finish it off and say this is all matrices. This A is a member of the collection of the family of matrices that are 2 by 3 that have integer entries. Also, you could say get a little bit fancier and say the collection of all 2 by 3 matrices that have integer coefficients is really just a subset of the collection of all matrices that are 2 by 3 that have real number entries. Why? Because anything that is an integer is also a real number. So all of this would be contained in that bucket. This is a much, much larger bucket. And also there's the number of rows and the number of columns could be any whole number. You could have a 1 by 3 matrix or 3 by 1. So let's say, or 1 by 2, for example, or 2 by 1 here. So we could have x and x squared plus 1. That right there is a matrix. And this would be an element, let's say P is equal to all polynomials. Let's just say that P is this collection of all polynomials with x as x variable. Okay, then I could say that this is a collection of member in the set of all matrices that are 2 by 1 that have polynomial entries. So this would be another example. That's how we define matrices, and that's the common notation. Okay, next, we want to learn how to add matrices. This just gives you a summary of what I just said. This is an m by n. Of course, the n is the number of columns. That's the second number. The m is the number of rows. The entries here, they all get named. For example, the A2 entry, sorry, the A23 entry, it's named that way because it's the entry on the second row, third column. This one, on the other hand, is the entry that's on the third row, first column. That's why it's called A31. So that's how we name every individual one of these entries. That's how you name the matrix. That's what we just got done doing. Matrices. What we want to do is define addition on these matrices. So how do you add things in the matrix? Well, I guess that most of you are here and you've already taken calculus, which means you already taken basic algebra, whatnot. So chances are you already know how to add matrices. But just in case, here's how you, in case you haven't, or in case you aren't from around here, I'll tell you how to do it. It's super, super simple. It'll take me like 5 seconds to show you how to do it. The thing to note here is that we only add numbers that have the same dimension. 2 by 2 can only be added with a 2 by 2. And of course, the same sort of creature inside here, because you got to add those creatures. So if these are real numbers, I got to be able to add real numbers. So you can't add real numbers in something that doesn't add with real numbers, like colors, for example. You can't add 2 plus red, but you could add 2 plus 1. So as long as you have the same, these are compatible, we could add them. And the way we're going to add them is real simple. All you do is take the 1, 1 entry and the 1, 1 entry, and you add them, and you get 3. Then you get the 1, 2 entry and the 1, 2 entry, and you add them. And so on and so forth. You add the 2, 1 entry, and then you add the last entry. And that's how you add matrices. Can't believe I get paid to do this. Insane amounts of money to do that. You add them, what you would call this is you add them component-wise. Okay, that's how you add them. You might also have had experience adding stuff like this when you added vectors. I'll give you another example. Back in trig or some other class, you might have added vectors like 2, 3, 1, added to 1, 1, 1. You could add these two, and again, you add them component-wise. Real simple like this. So the addition is super, super basic. The addition element, or sorry, the identity element is 0. So for example, if I have 2, 1, 1, 1 added to 0, 0, 0, 0, I'm guessing nothing's going to happen to that first matrix. I'll get 2, 1, 1, 1. So that guy right there is called the additive identity. Additive identity. In the world of matrices that are 2 by 2 that have real numbers. Okay, that's the additive identity. Doesn't change anybody. Okay, that's how you add. Multiplying is a little bit more complicated, but not that much. Again, I'll go through it assuming that most of you have seen it once or twice in your life. So the way you add them is you first look at you go by rows by columns. This is how we multiply the row. We multiply this row by this column. That's the first thing you got to do. So if I multiply this row times this column, and the way you do it is you do it using what you might have done before, the dot product. You get the 2 times the 1, that's 2, and the 3 times the negative 1, that's negative 3, and add it together, that gives you negative 1. And so I'll make a little think bubble here for the first entry. I'm doing 2 times 1 plus 3 times negative 1. And of course, that's going to give me negative 1. That's my first entry. For the next one, I'll take the same row times the other column. It's always row times column like that. And you're doing dot product. You might have done dot product before, like in a trig class or something like that. So for the dot product for these two, the first thing you would do is you take the 2 and that 2, that gives you 4. The 3 and the negative 5 gives you 15. So I'll make a little thinking bubble here to show you what I'm thinking for the second entry in the first row. 2 times 2 plus 3 times negative 5. Okay, so I'm thinking 4 plus negative 15. Okay, and so on and so forth. The next one, that's the first row of the product. For the second one, I'm going to use the second one times that, and the second one times that, and those will be my entries that go here. So the first one I do that. I'm not going to make a thinking bubble right now. I'll just think out loud. That's going to be -1 and a -4. So that's going to give me a -5. And then I'm going to do a negative that times that. I'm going to be doing it in my head. That's going to be -2 and -20. Okay, that's it. That's how you multiply matrices. Okay, the other thing that you got to note about multiplying matrices is that they don't have to be the same size to multiply them together. You could multiply things that are like this. You could multiply a 2 by 3 times a 3 by 2 matrix, such as these ones. The thing you got to watch out for is just the only number that has to match is this one. This one, the number of columns on this one must match the number of rows on this one. So as long as these two match, you'll get a good, they're compatible. And the resulting matrix will be this size, whatever this number is, by that number. That would be the result. So in this case, if I multiply these two, I'll get a 2 by 2 matrix. Okay, and the way we're going to do it is very, very similar to what we did before. Just take rows times columns. First, I'm going to do this row times this column. And I'm going to do it using the dot product, and I'll do it in my head. So I'm going to be taking that 2 times that 2. That's a 4. I'm going to take the 1 by that. That's a 3. I'm going to take that by that. That's a -4. So I'm going to be thinking, for the first one, I'm going to be thinking 4 plus a 3 plus a -4. That's going to give me a 3. So that's my first entry right there. Okay. Next, I'm going to be doing row times column. So I'm going to be multiplying the 5 by the 3, the 3 by the -1, and the -1 by the 0. And I'll add all of them up and see what I get. I'll write something here just to make sure we're all on the same page. This will give me a 10. This will give me a -3, and this will give me a 0. That's going to give me a grand total of 7. And so on and so forth. I'm going to multiply this one dotted with that one. That's going to be a -2 and a 4. That's going to give me 2. So this is going to give me 2. And then finally, I'm going to do this one times that one. That's going to give me -5 and a -4. That's -9. Zeros are going to kill each other. So I reckon I'm going to get a -9 here. And that's it. Now notice what happened here. Keep an eye on the dimension. As I said before, to be compatible, these numbers must match. And of course, these things have to be compatible too. You must be able to multiply them. But these numbers have to match the inner ones, and the result will be the outer ones, the 2 by 2. So in here, we have a 2 by 2 matrix as promised. Okay, that's how you multiply them. Now, I should mention maybe a larger, I don't know, you might think sometimes it's, if you're a beginner, you might wonder, why the hell would you multiply matrices that way, right? I wonder that sometimes. Or is there a more broader point of view that you can take to see what the hell we're doing here when we're multiplying them? A good way to think about it is, I think, well, here's another way to look at it, okay? For the first row, the 2 and the 3 here tell me that I'm going to take 2 of these ones and 3 of those, and I'm going to add them together, and I'm going to replace them right here. That's what it's saying. 2 of the first rows, 3 of the second rows, and I'm going to combine those guys. Is like making a mixture of the top row and the second row. I want myself a mixture of this and this. Like when you go to the store, I want 2 tomatoes and 3 oranges, whatever. I want 2 of these and I want 3 of these, and I want to combine them and put them here. Let's think that thoroughly. So if I want 2 of these ones plus 3 of these ones, that would give me, that's the same thing as saying 2 and a 4 plus a -3 and a -5. That's a -1 and a -1. So this is -1, -1. That's what it's equal to if I was to combine 2 of these plus 3 of those. All right. Of course, I did it wrong, but that's okay. Negative 3 should be negative 15. Don't worry about that. Details. Okay, okay. The other thing too is, of course, if you wanted to do this, that's telling me that I want negative 1 of these rows and I want 4 of these ones. So the way you'd cook that up is, okay, I want negative 1 of these ones plus I want 4 of these ones. That would be negative 1, negative 2 on the top, and that would be negative 4 and negative 20 on the bottom. If I add them, it's going to give me negative 5 and a negative 22. So this is going to be negative 5 and a negative 22. This would be another way to think about it. It's a much broader, more deeper way of thinking about multiplication of matrices. If you wanted to do that, same thing here. This is saying, hey, I want this many of these ones. I want 2 of these. I want 2 of these, 3 of these, and negative 1 of these. And I want you to put them there. Perfect. This one is saying I want negative 1 of these, 4 of these, and 0 of these, and put it here. And that's what that thing is doing. Okay, so that's just a slightly broader point of view on matrix multiplication. Of course, the identities are easy, and these identities will work for, they're usually just referred to when we have square matrices. Square means the number of rows and the number of columns are the same. This is the additive identity. It doesn't change anyone when you add to it. This is the multiplicative identity. It won't change. It won't change anything because it'll just take one of the first row and one of the second row, so it'll just leave it alone. That's vocabulary. Pretty much all the things that we learned before about integers, commutativity law, associativity law, all these all work except commutativity law of multiplication. This one will fail for matrices. Okay, it will fail miserably. And also inverses. Not all our matrices will have multiplicative inverses. Some of them you just can't invert them. So a couple little things to watch out for. This one may fail sometimes. This one may fail sometimes. All the other ones, good to go. Okay. But amazingly, with some of those failing, some of these theorems will also fail. It'll cause them to fail. So you have to be super, super careful. So whatever you did in algebra class here does not necessarily translate into matrices, which means you got to be extra cautious. Okay. Okay, let's pause here for a second. All right, so now let's talk a little bit about matrices. So again, or sorry, about inverses. So for regular numbers, recall that inverses are pairs of numbers that more or less kill each other and give you the identity. Take a look at this example. These are additive inverses, numbers that when you add them together, they undo each other and give you the additive identity. Multiplicative inverses are numbers that when you multiply together, basically kill each other and give you the multiplicative identity. So they're the yin and the yang. They undo each other when you perform that binary operation on them, and they give you the identity for that specific binary operation. Additive inverses give you additive identity. Multiplicative inverses give you multiplicative identity. And so too for matrices. We will say that matrices A and B are inverses, multiplicative inverses, if and only if, this is how you spell if and only if, A times B is equal to identity, and B times A is equal to the identity. If they kill each other and give you the identity, we will call them inverses of each other. Okay? So here's an example. What would be the inverse of that? Well, to find the inverse of that, I would need to find another matrix here. Let's just call it A, such that when I multiply them together, I get the identity 1, 0, 0, 1. If I could find that number here, then I could find the inverse of that matrix. So same thing here. I want to know what that times what gives you the identity being 1, 0, 0, 1. So here's maybe I don't want to go into that in detail right now, but here's a proposition. What if I told you those two are inverses? We could check to see if they're really inverses. Let's check. All we do is perform the multiplication. We're going to do that row times that column. So the 2 times the 4, that gives you 8. Take away 7, that gives you 1. Then we'll do this row times that column. 7 times 7, that's 14, and then the negative, that gives you 0, and so on and so forth. And these are indeed inverses of each other. So the answer is yes, these are multiplicative inverses. If this guy's called A, then that one is called A inverse, sometimes written like this, A with a negative 1. And we say that A times A inverse is equal to the identity. Okay. Similarly, you can check to see if these are inverses. Multiplying this row times that column, that would give us how much? It would give us 3 times 4 is 12. 12, and then negative 7. Actually, I think this should be, so let me just do that. That's 12 over 19 plus 7 over 19 when you do this one times that one. Sorry, let me clean it up a little bit so it looks prettier. And in fact, that gives you 19 over 19, which is equal to 1. Then we try the next one. This row times that column. The 3 and the 7 are going to give you 21, and the 3 and this 7 is going to give you 21. But this one's positive, this one's negative. That's going to give you 0, and so on and so forth. And so these, in fact, are multiplicative inverses of each other. That's how you check. Now, it doesn't explain how we found them, but for sure it explains how we can check to see if two things are inverses of each other. We'll talk more about how to find them later. Okay, I want to emphasize this thing I said earlier. These things do not, the matrices do not commute. This part right here fails, and sometimes they don't have an inverse. Those two things fail. So I want to really, really emphasize that there's no commutativity for multiplication. There is for addition, but not for multiplication. Not all inverses, not all matrices have an inverse. There's no zero factor theorem, and I'll talk a little bit more about that. But let me emphasize this one for now. So I took this matrix times that one, and then over here, I wanted to know, compare them, what happens when you switch them around. Should I get the same number? This would be analogous to thinking about, in the real number line or in the wheel of real numbers. Let me just make a thinking bubble here. If I do 3 times 5 versus 5 times 3, what do I get? Well, if I do 3 times 5, I get 15, but if I do 5 times 3, I also get 15. So in the world of real numbers, it doesn't make a difference. Real numbers commute. They commute under multiplication, and I'm trying to play with this idea in the world of matrices. If I have a matrix here times a matrix there, and then I switch them, as I have here, will I get the same answer? And so we go on and we multiply these and check, just for fun. It wouldn't prove anything if they happen to be the same, but it could prove that it doesn't work if they're different. So we start off with this row times that column. That would be a 2 and a negative 3. Then I do this row times that column. That would be a 4 and a negative 15. And similarly for the bottom, I get a negative 1 and a negative 4, and I get a negative 2 and a negative 20. Now if I do it the other way, backwards, I get a 2 and a negative 2. Already this is different. It fails miserably already, and I get 11 over here, and I get negative 2 and positive 5, and I get negative 3 and negative 20. So these matrices are totally different. It's analogous to if the numbers in real numbers. Imagine if 3 times 5 was 15 and 5 times 3 was something totally different. It can't happen in the real numbers. It happens all the time in the world of matrices. Okay. Also note that no matter how hard you try to find something here that gives you the identity, this will never happen. There is no inverse of this Does not exist. There's no A times, there's nothing here that would fit such that when you multiply them together, you get the identity. By 1, I don't really mean 1. Sometimes people will write 1, but what they mean is the identity, which is this one. If the context is clear that they were talking about a matrix, that's your quote-unquote 1. And this will fail miserably in this case. And it might be an interesting exercise to think about why that would fail. We could just try all the possible matrices in the entire universe and test each one and see that they fail. Or it could be a little bit smarter about it and see why. Suppose, let's just practice our proving techniques just for some fun. Suppose B is the inverse of A. B has to be equal to something like this. A, B, C, D. Then A times B must be equal to the identity. So that means that 0, 1, 0, 0 times A, B, C, D, numbers that I don't know, have to be equal to that, right? That would mean that, well, I could multiply these things on the left. That would mean, I'm thinking here, that times that, that's 0 A's and 1 C. Then I'm thinking this times that. Whoa. I'm thinking this times that. So I'm thinking 0 B's and 1 D. So that would be a D. And then on the bottom, that gives me 0. And that gives me 0. So that tells me that now if these two matrices are the same, that has to be the same as that, that has to be the same as that, that has to be the same as that, and that has to be the same as that. That means that C must be equal to 1, D must be equal to 0, 0 must be equal to 0, and 0 must be equal to 1. Does anyone see a problem here? This leads to a clear contradiction here. There's no value of A, B, C, and D that make 0 equal to 1. It's just not happening. And so this would be the symbol for contradiction, and therefore B does not exist. And I just proved that this matrix A has no multiplicative inverse in the entire universe of all matrices. There's no matrix that could kill A and give you the identity. Okay, so just be careful. Everything changes in matrices. The commutativity, things don't have multiplicative inverses. Also, the zero factor theorem is out of the question. See, if you have two real numbers and A times B is equal to 0, for example, I tell you I have something here times something here is equal to 0. These couldn't be both non-zero. That would never work. 3 times 5 is -0. At least one of them has to be equal to 0, then it would work. That's why when you were solving equations such as x minus 3 times x plus 5, you could exploit this fact and say, oh, x minus 3 must be equal to 0, or x plus 5 is equal to 0 because of the zero factor theorem. And then you could go on and solve that equation. Yeah, none of that works here. You could have non-zero, two numbers that are both non-zero, and they multiply together and give you 0. So the zero factor theorem fails in the world of matrices. Also, simple things like this, like a regular polynomial. You did this in high school where you FOIL this. The way you actually did it was something like this. I'll go through the steps for this. If you have x plus y squared, well, that would be x plus y times x plus y, right? And you could take this number, this whole quantity, and distribute it to the x and distribute it to the y. So that could become x plus y times x plus y times y using the distributive law. That become x times x plus y times x plus x times y plus y times y. And that could become x squared plus yx plus xy plus y squared. Now here's the difference between regular polynomials and matrices. In regular polynomials, sorry, in regular numbers, these two numbers are the same because for real numbers, x times y is the same thing as y times x. And so I could just combine these and say, by the way, this was the distributive law. I could prove this using good stuff from our axiom sheet, from this sheet. Distributive law, this was distributive law. This was definition of exponents. Here's the crucial part. This is equal to x squared plus yx plus yx. I changed this one right here into yx plus y squared, or I could change the other one into xy just so I can match that. Hold on, sorry. This becomes xy plus xy. So now I changed this one, and that would be by commutativity law of multiplication, right? And then I could just say x squared plus 2xy's plus y squares. The trouble with matrices is that you don't get this step right here. They're not commutative. I just show you examples of matrices that don't commute. These guys fail miserably. So this step would fail in the world of matrices. And so in the world of matrices, the correct statement, for example, if you have a plus b squared, that would be a squared plus ab plus ba plus b squared. That would be true, not this. Well, it wasn't even true to begin with. Okay, I meant to have a 2 there. All right, so the point here is be careful. Everything that was true for real numbers does not necessarily translate to matrices. Okay, that's the whole point of this. Another thing to look for is solving equations in algebra, and how does that compare with matrices? Let's say we wanted to solve this using super careful steps back from algebra. The thing that you could do is you could slap an inverse on both sides. I'll slap an inverse on this side. I'll slap an inverse on that side. That would be cancellation law of multiplication. I can multiply both sides by something. The next step that I could take would be maybe I can reassociate them. 1/3 times 3 times x is equal to 1/3 times 10, whatever. So that's associative law of multiplication, where I've taken these parentheses and I slided them this way to cover only the 1/3 and the 3. That's why it's called associative law of multiplication. And of course, these ones give you 1 because they're multiplicative inverses. And of course, this gives you just x because that's the multiplicative identity. 1 doesn't change any 1 when you multiply by it. Now it turns out how many of these we want to ask, how many of these steps could you mimic in the world of matrices? If I have a matrix A times some other matrix, some unknown variable x. Wow, I'm running out of ink. Unbelievable. Let me pause this. All right, so I was saying that we could imagine the exact same scenario here, but with matrices, meaning that we could have a matrix A times some other matrix X that we don't know is equal to some other matrix B. Amazingly, the exact same steps that we did here on the left-hand side would also work on the right-hand side. So one way to solve matrix equations would be to take your B here, take your A here, and slap a A inverse on both sides, A inverse, assuming such a beast exists. And that would be called cancellation law of multiplication, where you multiply both sides by a matrix. That would be okay. Associativity is still okay, so I can go on and take these parentheses and just move them this way so that I can associate these two things, giving us something like this: A inverse times A times X, and moving the parentheses this way. And that would be associative law of multiplication. That still works in matrices. Of course, these give you the identity matrix, and that gives you A inverse times B. These are multiplicative inverses. And of course, the identity times any number is just itself. That's multiplicative identity. So exactly the same steps that you would have taken in your third grade algebra class will work here in linear algebra with matrices. And really what that would look like would be maybe something like this. I'll give you a more concrete example. Suppose I have, let me see, I'm going to take one of these ones that I already knew here. Where are my inverses? 4, 7, 1, 2. 4, 7, 1, 2. And I'm going to multiply times another matrix xy. And I'm going to tell you that's equal to -1, 5. Now, I'll ask you, how do you solve that? Well, just imagine this is your matrix A, this is your X, and this is your B. We want to slap A inverse on both sides, and that would get this on the other side. So you could say that if I could multiply both sides by, it's so tempting to just do it. I guess I'll just have to do it. Can't stop now. So I'm going to take the inverse of this guy, 4, 7, 1, 2, whatever it is, and I'm going to slap it on both sides. 4, 7, 1, 2 inverse. And I'm going to do this, that's called cancellation law of multiplication. And exactly the same steps. These ones are going to be inverses of each other. So I'll just get, and I'm going to have associativity law and all that other good stuff, all the steps above. And in the end, I'll have something like this. I'll have that the xy is equal to the inverse of that times that. And of course, I already knew what the inverse is because we talked about this earlier. The inverse of that guy is that guy. The 2 and the 4 and the other numbers change. And so this means that, I'll continue here, that xy is equal to 2, 7, -1 times -1, 5. So xy is equal to, now I'm going to multiply that many, that times that, and that times that. That's going to give me -2 and a -5, 1 and a 35. And there you go. I finished the equation. So all these steps that you did in basic algebra could also work in matrices. Amazingly, if you did the left-hand side of this, if you did that before you go into all this fancy stuff, it would actually look like this. It would look like 4x plus 7y, and it would look like 1x plus 2y. That's what happens when I multiply that times that and that times that. And that's equal to -1 and 5. So this actually is a system of equations. You turn it into a matrix equations. You do some fancy thing where you slap an inverse on both sides, and you get the solution in the most fancy way in the entire universe. It's kind of beautiful. This would be called solving systems of equations using matrices and inverse matrices. Okay, so that's just a little taste of it. Again, the point of this slide is you could solve any kind of equation you had this for plus, especially it will work the same way as for the matrix version of that would be the same as the algebra version of it. What you did in algebra in third grade. Okay, so yeah, this explains what I just did. This tells you that, of course, again, this tells you that this matrix 2x plus 5y x plus 2y, this matrix is equal to this matrix 5 and -2, because the only way they can be equal if piecewise they're equal. That has to be equal to that, and that has to be equal to that. But of course, the left side, this one can be broken up into the product of two matrices. This is 2, 5, 1, 2 times xy, and that's equal to 5 well, -2. And so using this fancy language, you could slap an inverse on both sides. It's beautiful. Okay. All right. I think that'll do it for now. It gives you a tiny, tiny little taste into matrices, their properties, the fact that they're not commutative, and how they can be used to solve equations. All right. We'll see you guys next time.